Welcome! In this session, we'll be exploring problem number 250, count Univalue Subtrees. This is an engaging problem that involves analyzing the structure of a binary tree to count the number of subtrees where all nodes have the same value. We'll break it down step by step and examine different approaches to solve it. Let's get started. In this problem, we are tasked with counting the number of univalue subtrees within a given binary tree. A univalue subtree is defined as a subtree where all the nodes share the same value. The input to the problem is the root node of a binary tree, where each node holds an integer value. The tree could also be empty. The output we need to return is an integer that represents the count of univalue subtrees within the tree. For example, consider the binary tree shown here. The root value is 5, and it has two children, 1 on the left and 5 on the right. The left child, in turn, has two children with the value 1, while the right child has a single right child with the value 5. This structure will help us understand how univalue subtrees are identified and counted. Here, we see the output and explanation for the first example. The output is 4, as there are 4 univalue subtrees in the given tree. These include the left child of the left subtree, the right child of the left subtree, the entire left subtree rooted at the value 1, and the right subtree rooted at the value 5. However, the root node itself, with a value of 5, is not a univalue subtree. This is because its left and right subtrees have different values, breaking the univalue condition. Now looking at another example, the binary tree is structured differently, with all nodes having the same value of 1. This setup provides another perspective on how to identify univalue subtrees. In this second example, the output is 6 because every part of the tree is a univalue subtree. Each individual node qualifies as a univalue subtree, as do the left and right subtrees rooted at the value 1. The entire tree itself, rooted at the value 1, is also a univalue subtree. Since all nodes share the same value, every possible subtree satisfies the univalue condition. This demonstrates how the total count of univalue subtrees can increase significantly when the values are uniform across the tree. Next, let's consider the constraints and edge cases that can arise with this problem. The problem comes with clear constraints. The number of nodes in the tree can range from 0 to 10,000, and the values of the nodes lie between -1,000 and 1,000. Notably, an empty tree is defined as having 0 univalue subtrees. A single-node tree, on the other hand, has exactly one univalue subtree because the single node itself forms a valid subtree. Additionally, if all nodes in the tree share the same value, every subtree, including the entire tree, will qualify as a univalue subtree. However, if the root has a value that differs from its children, the root cannot be part of a univalue subtree. Even so, its children and their respective subtrees might still meet the univalue condition. These considerations will guide us in formulating and implementing a robust solution. To begin tackling this problem, one intuitive approach is to use a brute force method with naive recursion. The idea here is straightforward. For every node in the tree, we examine its entire subtree to determine if all the nodes within it share the same value. If they do, we count this subtree as a univalue subtree. This involves recursively traversing the subtree of each node and verifying the univalue condition. While this method is simple to implement and easy to understand, it has some notable inefficiencies. Specifically, the time complexity is O(n squared), as we end up repeatedly traversing subtrees for each node, leading to redundant computations. The space complexity is O(h), where h represents the height of the tree, due to the recursive stack. While this approach is a good starting point, it doesn't leverage the tree's structure to optimize the process, making it less practical for larger trees. To address the inefficiencies of the brute force method, we can use an optimized approach that leverages post-order traversal with bottom-up validation. This strategy eliminates redundant checks by processing the tree in a way that ensures each node is considered only once. The key insight here is to validate whether a subtree is univalue as we backtrack from the leaf nodes up to the root. For instance, a leaf node is inherently a univalue subtree since it has no children. For non-leaf nodes, we check two conditions. First, whether both the left and right subtrees are univalue. Second, whether their values, if they exist, match the current node's value. By following a post-order traversal, where we process the left child, the right child, and then the node itself, we ensure that every subtree is validated only once. This significantly reduces redundant computations and makes the algorithm much more efficient. This optimized approach offers a substantial improvement in complexity. The time complexity is O(n), as each node is processed exactly once during the traversal. The space complexity remains O(h), where h is the height of the tree, due to the recursive stack. Given these factors, the optimized approach is the appropriate strategy for this problem. It not only achieves linear time complexity but also aligns well with the problem's bottom-up structure, making the implementation clear and intuitive. However, there are trade-offs to consider. For instance, the reliance on recursion could lead to a stack overflow for extremely deep trees, though this can be mitigated by rewriting the algorithm iteratively. While this method requires a stronger understanding of tree traversals, its efficiency and scalability make it the ideal choice for solving this problem, particularly for larger trees. Overall, this approach balances simplicity and performance effectively. The problem we're addressing is to count the number of Univalue subtrees in a binary tree. A Univalue subtree is one where all nodes within it share the same value. For example, a single node is always considered a Univalue subtree, and if all nodes in a larger subtree have the same value, that subtree qualifies as well. The challenge lies in computing this count efficiently for the entire tree. To start, we can consider the brute force approach using naive recursion. The idea here is to define the subproblem. For each node in the tree, determine if its subtree is a Univalue subtree. To do this, we traverse the subtree rooted at the current node, verifying that all its nodes share the same value. This involves designing a recursive helper function, is_Univalue_tree, which checks the validity of the subtree by comparing the current node's value with its children. The base case for this function occurs when the node is null, at which point we return true, since an empty subtree is trivially Univalue. In the recursive case, the function checks both the left and right subtrees and verifies whether the current node itself contributes to a Univalue subtree. To complete the brute force approach, we add a mechanism to count the number of Univalue subtrees. This is done by maintaining a global counter that increments each time the helper function confirms a subtree is Univalue. The final result is obtained by traversing the entire tree and returning the total count stored in this counter. Recursion is particularly well suited to this problem because the process of determining whether a subtree is Univalue can be naturally divided into smaller subproblems for the left and right children. This mirrors the hierarchical structure of the binary tree itself. There are, however, important edge cases to consider. For instance, a tree with just one node is always a Univalue subtree. If all nodes in the tree share the same value, then every subtree qualifies. Conversely, if no two nodes share the same value, only the leaf nodes will count as Univalue subtrees. While the brute force approach is functional, it is not optimal, as it may traverse the same nodes multiple times. This inefficiency can be addressed through optimization. By shifting to a bottom-up approach, we eliminate the repeated traversal of nodes seen in the brute force method. In this optimized strategy, we ensure that each node is visited only once. The hierarchical structure of the binary tree remains central, and we use two key data structures to implement the solution. First, the binary tree itself naturally represents the problem structure, with each node containing a value and pointers to its left and right children. Second, we use a global counter to efficiently track the count of Univalue subtrees. The optimized algorithm involves defining a new recursive function, count_Univalue_subtrees. If the current node is null, the function returns true, as an empty subtree is trivially Univalue. Otherwise, we recursively determine whether the left and right subtrees are Univalue. Then, we check whether the current node forms a Univalue subtree by comparing its value with its children, if they exist. If the subtree rooted at the current node is confirmed to be Univalue, we increment the global counter. The recursive function then returns whether the subtree rooted at the current node is Univalue. To ensure correctness and efficiency, post-order traversal is used. This traversal strategy processes the left and right subtrees before evaluating the current node, ensuring that every smaller subtree is validated before its parent. In terms of computational complexity, this approach is highly efficient. The time complexity is O, n, where n is the number of nodes in the tree, since each node is visited exactly once. The space complexity is O, h, where h represents the height of the tree, as this is the maximum depth of the recursion stack. The algorithm is implemented in Python using a helper function that encapsulates the recursive logic. By maintaining a global counter and leveraging the bottom-up strategy, the function avoids redundant computations. This ensures that the solution is both elegant and efficient, meeting the problem requirements within optimal constraints. The implementation concludes with the helper function returning true or false to indicate whether the subtree rooted at the current node is Univalue. If it is, the global counter is increment. Finally, the main function invokes this helper on the root of the tree and returns the counter's value as the total count of Univalue subtrees. Key operations include post-order traversal, which ensures smaller subtrees are evaluated before their parents, and value comparisons at each node to determine whether the subtree is Univalue. The global counter eliminates the need for redundant computations at higher levels of the tree. This bottom-up approach works because it guarantees that every node is processed only once, and by evaluating smaller subtrees first, we avoid unnecessary re-evaluation. Together, these techniques minimize memory usage and computation overhead, providing a clean and efficient solution to the problem. Here, we begin by defining a basic tree node class to represent each node in the binary tree. Each tree node has a value, a left child, and a right child. Then, we define our solution class, which contains the main method, countUnival Subtrees. Inside this method, we initialize a counter, self.count, to keep track of the number of Univalue subtrees. Next, there's a helper function, is_Univalue_subtree, which is defined to determine if a given subtree is a Univalue subtree. This function starts by checking if the current node is none. If it is, we return true because an empty subtree is considered Univalue by definition. Otherwise, we recursively check the left and right subtrees to determine if both are Univalue subtrees. Once we know whether the left and right subtrees are Univalue, we proceed to check the current node. If both subtrees are Univalue, we further verify if the current node's value matches the values of its children, if they exist. If there's a mismatch, we return false. Otherwise, we increment the count, as the current subtree is confirmed to be Univalue, and return true. If either the left or right subtree is not Univalue, we immediately return false for this subtree. Finally, the helper function is called on the root node, and the total count of Univalue subtrees is returned as the result. This structure ensures that we traverse the entire tree and correctly count all Univalue subtrees. Here, we start by defining the tree node class, which represents the basic structure of a binary tree node. Each tree node has an integer value and pointers to its left and right children. The constructor initializes the node's value, and by default, both children are set to null. Next, in the solution class, we declare a private integer variable count to track the number of Univalue subtrees. The main method, countUnival Subtrees, takes the root of the tree as input and calls a helper method, isUnivalue Subtree. This helper method is responsible for determining if a given subtree is a Univalue subtree. Finally, the count of such subtrees is returned. The helper method begins by checking if the current node is null. If it is, we return true since a null node is considered a Univalue subtree by definition. Now, we move on to recursively examine the left and right subtrees. The helper method continues by recursively calling itself on the left and right children of the current node. The results are stored in the variables left_isUnival and right_isUnival. If either of these subtrees is not a Univalue subtree, the current subtree cannot be Univalue, so we return false. Next, we check if the left child exists and has a value different from the current node's value. If this condition is true, the current subtree is not Univalue, and we return false. Similarly, we perform the same check for the right child. If the right child's value differs from the current node's value, we return false. If none of these conditions are met, it means the current subtree is Univalue. We increment the count variable to include this subtree and return true, indicating that the current subtree satisfies the Univalue condition. To begin, we start with the simplest example, a single-node tree where the root node has the value 1. First, we initialize the count of Univalue subtrees to 0. Then, we call the helper function is_Univalue_Subtree with the root node as the argument. Since the root is not null, we proceed to check its left and right children. Both the left and right children are null, so when the helper function is called with these null nodes, it returns true, indicating that null children are considered univalue subtrees. Next, we check if both the left and right subtrees are univalue, which they are, and since the current node has no children, the subtree rooted at this node is considered a univalue subtree. We increment the count to 1 and return true to indicate that this subtree is univalue. The final result is that there is one univalue subtree in this tree, which is the single node itself. Now we expand to a slightly more complex example, a 3-node tree where the root has the value 1, and both its left and right children also have the value 1. As before, we initialize the count to 0 and call the helper function with the root node. The function recursively processes the left and right subtrees. For the left child, which has the value 1, we again recursively check its children. Since both children are null, they return true, and the subtree rooted at this node is identified as univalue. The count is incremented to 1, and we return true. Similarly, for the right child, which also has the value 1, its null children return true, making this subtree univalue as well. The count increases to 2, and we return true. Finally, at the root level, we confirm that both the left and right subtrees are univalue and that their values match the root's value of 1. This means the entire tree is univalue, and we increment the count to 3. With the entire tree confirmed as a univalue subtree, the final count is 3. This means there are 3 univalue subtrees in total, the left subtree, the right subtree, and the entire tree itself. The output for this example is therefore 3. This highlights how the algorithm effectively identifies univalue subtrees at each level of the tree and combines these results to determine the overall count. In this final example, we examine a mixed tree where the root has the value 1, the left child also has the value 1, but the right child has the value 5. Additionally, the left child has 2 subtree children, both with the value 1. We start by initializing the count to 0 and calling the helper function on the root. For the left child, we process its 2 children. Each of these subtrees is univalue because their children are null, so we increment the count to 2. Since both children of the left subtree have values matching their parent, the subtree rooted at the left child is also univalue, and we increment the count to 3. For the right child, which has the value 5, its null children make it univalue as well, so the count increases to 4. Finally, at the root, we check if the left and right subtrees are univalue. While the left subtree is univalue, the right subtree's value does not match the root's value, so the entire tree is not univalue. The final count remains 4, and the output for this example is 4. The time complexity of the count Univalue Subtrees function comes down to 2 main components. First, the recursive traversal of the tree. The helper function is_Univalue_Subtree uses depth-first traversal, meaning it processes each node in the binary tree by visiting its left and right child nodes recursively. Because each node is visited exactly once during this traversal, the time complexity for this part is O(n), where n is the total number of nodes in the tree. Second, for each node, the algorithm checks whether it forms a univalue subtree by comparing the values of its left and right child nodes to its own value. This check involves a constant amount of work, or O(1), per node. When we combine these two observations, we see that the overall time complexity of the function is O(n), as the traversal dominates the constant time operations at each node. The space complexity of the algorithm is primarily determined by the memory used for the recursive call stack during the depth-first traversal. The depth of this recursion is proportional to the height of the binary tree. In the best-case scenario, where the tree is perfectly balanced, the height is O log n, and so the space complexity is O log n as well. On the other hand, in the worst-case scenario, which occurs when the tree is completely skewed, the height of the tree becomes O(n), and the space complexity increases to O(n). Additionally, the algorithm uses only a constant amount of extra space for variables like self.count and the Boolean values returned by recursive calls, which contributes O(1) to the space complexity. Therefore, the total space complexity is O(h), where h is the height of the tree, ranging from O log n in the best case to O(n) in the worst case. When comparing this approach to a brute force method, the efficiency of the algorithm becomes even more apparent. A naive approach would involve evaluating every possible subtree of the binary tree to determine if it is a univalue subtree. Since a binary tree can have n squared possible subtrees, the brute force method would have a time complexity of n squared. In contrast, the current algorithm avoids this inefficiency by leveraging depth-first traversal, which ensures that each node is processed only once, achieving an n time complexity. Now, looking at the best, average, and worst-case scenarios, the time complexity remains n in all cases because every node in the tree is always visited. However, the space complexity varies depending on the tree's shape. In the best case, where the tree is balanced, the recursion depth is log n, leading to a space complexity of log n. In the average case, for a randomly structured tree, the height is generally log n, so the space complexity remains log n. In the worst case of a completely skewed tree, the recursion depth equals the total number of nodes, resulting in a space complexity of n. To solidify our understanding, let's discuss the proof of the big O notation. The algorithm processes each node exactly once during the depth-first traversal, and at each node, it performs a constant amount of work. This means the total amount of work done is directly proportional to the number of nodes in the tree, giving the algorithm a time complexity of n. For space complexity, the recursive call stack is the primary factor. The memory usage depends on the height of the tree, which is h. For a balanced tree, the height is log n, leading to a space complexity of log n. For a skewed tree, the height becomes n, and the space complexity increases to n. In conclusion, this algorithm is highly efficient, with a linear time complexity and a space complexity that scales with the height of the tree, demonstrating its suitability for handling both small and large binary trees effectively. A common mistake when solving tree problems is not accounting for edge cases, such as handling empty trees or single-node trees. These cases are important because if you neglect them, your code might crash or produce incorrect results. To avoid this, always make sure to include base cases in your recursive or iterative implementation. Another issue is inefficient tree traversal. A naive approach might traverse the same subtrees multiple times, leading to a time complexity as high as n squared. Instead, you can optimize this by using memoization or adopting a bottom-up approach, which avoids redundant calculations. Additionally, when dealing with subtree properties, it's crucial to verify all constraints, like checking if a subtree is univalue or satisfies binary search tree properties. Failing to do so often leads to incorrect outputs. To tackle this, make sure your helper functions return clear and complete information about the subtree. Lastly, overcomplicating the recursive solution is another pitfall. If you add unnecessary conditions or variables, your code becomes harder to understand and debug. Simplify your recursion by focusing on what each subtree should return and avoid introducing excessive complexity. Sometimes, iterative solutions are required, especially when recursion depth is a concern. For example, deep recursion can lead to stack overflow errors. In these cases, it's essential to understand and practice iterative tree traversal techniques, such as using stacks for depth-first search. Shifting gears to interview preparation, pattern recognition is a critical skill. Many tree problems, whether it's counting subtrees or validating binary search trees, often follow similar recursive patterns. Mastering these patterns and understanding bottom-up traversal will help you tackle a wide range of problems. Another tip is to communicate your thought process during interviews. Explain your approach clearly, highlight the time and space trade-offs, and discuss how you handle edge cases. This shows that you're thinking in a structured and deliberate way. Be prepared to discuss both recursive and iterative solutions, especially if the interviewer asks about recursion depth issues. They might even challenge you to implement an iterative version to test your grasp of stack-based algorithms. Finally, reducing a problem to simpler subproblems is key. For instance, when verifying subtree properties, you can focus on specific conditions in just the left and right subtrees, which simplifies the overall problem significantly. To deepen your understanding, there are several related problems worth exploring. Examples include LeetCode 250 for counting univalue subtrees, LeetCode 98 for validating a binary search tree, LeetCode 543 for finding the diameter of a binary tree, and LeetCode 112 for checking a path sum. Each of these problems shares common themes, like recursive traversal and subtree analysis. Now, considering alternative approaches, a naive recursion or brute force method involves checking each subtree individually. While this approach is straightforward, its time complexity can balloon to O(n) squared in the worst case, as it may recheck the same subtrees multiple times. For larger trees, this inefficiency becomes a significant drawback. A more efficient strategy is bottom-up recursion, where the tree is processed from its leaves toward the root. This method combines results from subtrees in a single pass, leading to an optimal time complexity of O(n) and a space complexity of O(h), where h is the height of the tree. However, bottom-up recursion requires careful handling of return values to ensure subtree properties are correctly combined. While it's faster, this approach does demand a solid understanding of how to structure recursive calls. Another approach is iterative depth-first search, which uses a stack to simulate the recursion process. This method has a similar time complexity of O(n) and space complexity of O(h), but it avoids issues related to recursion depth. However, writing and debugging iterative DFS can be more challenging, as you need to manage the stack explicitly and ensure all operations are handled in the correct order. A further alternative is breadth-first search using a queue. This technique processes the tree level by level, making it particularly useful for problems that require level-order traversal. Its time complexity is O(n), while the space complexity depends on the maximum width of the tree, denoted as O(w). While BFS can be helpful for certain tasks, it's generally less intuitive for problems centered on subtree properties, as it doesn't naturally align with recursive or bottom-up processing. Each of these approaches has its trade-offs, so it's important to choose the right one based on the problem requirements and constraints. Thank you for watching. Today, we tackled problem number 250, count Univalue Subtrees, breaking it down into manageable steps. We discussed the naive recursion approach and highlighted the importance of recursion in tree-based problems. Remember to practice similar problems to strengthen your understanding. Don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!